For most of its life, this was just a backyard. A house, a fence, a few trees. Nothing about it looked connected to artificial intelligence. And then, the infrastructure started getting bigger. Not robots, not servers, power lines. Across Northern Virginia, communities have been confronting new high-voltage transmission projects as one of the largest concentrations of data centers in the world demands more electricity. And that's the strange part. The AI boom is supposed to be happening inside computers, but increasingly, its consequences are appearing outside them, in substations, in transmission lines, in transformers, in power plants, and sometimes right beside people's homes. Because the next major constraint on artificial intelligence may not be artificial at all. It may be the physical world. To understand why, start here. Northern Virginia, just outside Washington, D.C. For decades, this region has quietly become one of the most important pieces of digital infrastructure on Earth. Loudoun County is home to one of the world's largest concentrations of data centers. From the outside, most of them are almost boring. Large rectangular buildings, few windows, no giant assembly lines, no obvious sign that anything extraordinary is happening inside. But electrically, these buildings are anything but ordinary. Modern AI infrastructure can concentrate enormous computing demand in a single location. Thousands, sometimes tens of thousands, of specialized chips operate around the clock. Those chips generate heat. Cooling systems remove that heat. Networking equipment connects the machines. Backup systems wait in reserve. And every layer depends on electricity. So while artificial intelligence feels almost weightless on a laptop screen, underneath it sits an increasingly enormous industrial system. And that system is growing very quickly. In 2024, data centers around the world consumed roughly 415 terawatt-hours of electricity. By 2025, the estimate was around 485. And in the International Energy Agency's central projection, global data center electricity consumption approaches 950 terawatt-hours by 2030, nearly twice today's level. But the important thing isn't simply that AI uses electricity. Everything uses electricity. The important thing is the speed. A new software service can reach millions of people in weeks. A new AI model can spread globally almost overnight. Servers can be ordered. Racks can be installed. More GPUs can be connected. But electrical infrastructure does not move at the same speed. A transmission project can take years. A substation can take years. New generation can take even longer. And some of the equipment connecting all of this together has become surprisingly difficult to obtain. That creates an uncomfortable mismatch. The AI industry can build computing demand faster than the physical system underneath it can expand. Software moves at software speed. Power does not. Imagine building an AI data center. You buy the land, you construct the buildings, you install the racks, you fill them with some of the most sophisticated computer chips humanity has ever manufactured. And then, you have to plug all of it in. Electricity has to move from generation through high-voltage transmission lines into substations, through switchgear, through transformers, and finally into the systems that feed the servers. For years, the obvious bottleneck in artificial intelligence was the chip. Could NVIDIA supply enough GPUs? Could semiconductor fabs produce enough advanced silicon? Could manufacturers supply enough high-bandwidth memory? But now, another class of hardware is becoming critical: transformers. Large power transformers are not glamorous. They rely on technology that has existed for generations: steel, copper, insulation, precision manufacturing. enormous pieces of electrical equipment built to survive for decades. And yet, some large transformers can now take years to procure. For certain units, industry lead times have stretched toward 3 or 4 years. Then, there is the grid connection itself. At the end of 2025, more than 2,060 gigawatts of proposed generation and storage were actively seeking connection to the U.S. grid. That does not mean 2,060 gigawatts of power plants are about to be built. Most projects that enter these queues never reach commercial operation. But the backlog reveals something important. Connecting new infrastructure to the grid is already slow, and enormous new electricity users are arriving at exactly the same time. The paradox is almost perfect. An AI company can buy machines capable of performing trillions of calculations every second and still spend years waiting for electrical infrastructure. Silicon is fast. Steel is slow. If this were a minor problem, the world's largest technology companies could simply wait for utilities to solve it. They aren't. Microsoft entered a long-term power agreement tied to the restart of the former 3 Mile Island Unit 1 in Pennsylvania, now called the Crane Clean Energy Center. Amazon has made major agreements involving nuclear power and has invested in advanced reactor technology. Google has signed deals connected to future nuclear projects, including reactors being developed by Kairos Power. Meta has also pursued major nuclear power agreements, but these projects are not all the same. Some involve existing nuclear plants. Some involve future reactors. Some are power purchase agreements. Some are investments. Some are still years away. And a contract announced today does not mean electricity is already flowing into an AI server tomorrow. Still, taken together, these moves reveal something remarkable. Companies whose most valuable products are software are increasingly securing physical energy infrastructure. Because electricity is no longer merely an operating expense. It is becoming strategic capacity. A company may have the money to buy GPUs. It may have the engineers to build models. It may have customers waiting to use them. But if it cannot secure enough electricity in the right place, at the right time, none of that computing capacity matters. The AI race is quietly becoming an energy race. And if waiting for the grid takes too long, there is another option. Build around it. Normally, electricity moves through a shared system. Generation, the grid, substations, then the customer. But a large data center can also pair itself with dedicated generation, power produced much closer to the load, sometimes behind the meter. Instead of waiting for the wider grid to deliver everything it needs, a facility can generate part of that electricity itself. In some places, that means natural gas. The appeal is obvious. If a company can secure dedicated power, it may avoid some of the delays involved in waiting for public grid capacity. But the shortcut creates its own questions. In the Memphis region, xAI developed enormous computing facilities for its Colossus systems and used large numbers of gas turbines as part of its power strategy. The NAACP later sued over the operation of turbines associated with the project. That is an active legal dispute, not a settled finding of liability. But the conflict illustrates something larger. What happens when the pace of AI construction runs into environmental regulation, utility rules, permitting, and communities living next to the infrastructure? Because a server can be installed quickly, a GPU cluster can expand quickly. Energy infrastructure belongs to a different world. Permits, engineering studies, equipment factories, utilities, regulators, courts, communities. AI moves at software speed. Power moves at infrastructure speed. But even when enough infrastructure eventually gets built, there is another question. Who pays for it? One of the most important places to watch is PJM. PJM coordinates the bulk power system across all or part of 13 states and Washington, D.C., serving more than 67 million people. One part of that system is the capacity market. The basic idea is simpler than it sounds. The grid doesn't only need enough electricity today. It needs confidence that enough power will be available during future periods of extreme demand. So resources can be paid for, committing capacity ahead of time. And recently, the price of securing that future capacity changed dramatically. For the 2024 to 2025 delivery year, the PJM-wide capacity price was about $29 per megawatt day. For 2025 to 2026, almost $270. For 2026 to 2027, about $329. And for 2027 to 2028, $333.44. That is a dramatic change, but it does not mean data centers alone caused it. The system is more complicated. Power plant retirements matter. Available supply matters. Transmission constraints matter. Market rules matter. And rapidly rising demand matters. PJM itself has repeatedly pointed to data centers as one of the major drivers of its load growth. Its independent market monitor has also argued that data center demand contributed substantially to recent capacity market pressure. Exactly how much should be attributed to data centers and how much comes from the other forces tightening the system is contested. And that is where a technical electricity market problem becomes a political one. If a new data center requires a substation, a transmission line, additional generation, or grid upgrades, how much of that cost belongs to the data center? How much belongs to the utility? And how much should be spread across everyone using the grid? There is no single answer. Different projects, different utilities, different states, different rules. But every dollar allocated somewhere eventually lands somewhere. And that takes us back to Northern Virginia. The infrastructure appearing around homes and communities is not abstract. Those towers have to stand somewhere. Those substations occupy real land. Those upgrades have to be financed. The cloud was never actually in the cloud. It was always land, buildings, wires, steel, and electricity. AI is simply making that physical reality much harder to ignore. There is, however, a serious argument that this problem could be overstated. AI is becoming more efficient. New chips can perform more computation for every watt. Models are being optimized. Inference can become cheaper. And every forecast of future data center demand depends on something nobody can know with certainty: how much AI the world will actually use. Some announced data centers may never be completed. Some proposed power projects may disappear. Some AI investments may fail. Companies may discover they purchased more computing capacity than customers actually want. And different regions can respond differently. Some may expand shared transmission. Some may build new generation. Some large users may bring more of their own power. Some may accept limits on when they can draw electricity from the grid. So the future is not predetermined. The largest forecasts could be wrong. But dismissing the entire problem requires ignoring something else. You don't need the biggest forecast to come true to see what is already happening. Transformers are already being ordered. Transmission projects are already being proposed. Technology companies are already signing long-term power agreements. Regulators are already rewriting and questioning rules for very large new electricity users. Communities are already debating where this infrastructure should go. The future may be uncertain. The collision has already started. On June 18, 2026, The Federal Energy Regulatory Commission issued show cause orders to all 6 regional grid operators under its jurisdiction. The question was no longer hypothetical. FERC wanted those operators to justify, or reform, the rules governing how enormous new electricity users, including data centers, connect to the grid. How should they be studied? How should reliability be protected? How should costs be allocated? And how can the system add enormous new demand without quietly shifting unreasonable costs somewhere else? PJM, meanwhile, continues to develop approaches for connecting and managing very large new loads. The process is still evolving, which means one of the most important questions in artificial intelligence is now being argued not only inside research labs, but inside electricity markets, utility planning rooms, and regulatory proceedings. For decades, computing became easier to scale because the physical complexity disappeared from view. Open a laptop, rent cloud capacity, run the code. Someone else dealt with a power station. Someone else dealt with a transmission line. Someone else dealt with a transformer. AI is beginning to reverse that abstraction. Its electricity demands are becoming large enough that the hidden infrastructure is becoming visible again. The AI race began as a race for algorithms. Then, it became a race for chips. Now, increasingly, it is becoming a race to build everything around those chips. Power plants, transmission lines, substations, transformers, land, permits, and time. Because software can scale in months, the electrical grid cannot. And the gap between those two clocks may determine what the AI boom becomes next.